Hey class, welcome to our online video as we start doing a few classes through the internet. Anyway, so we're going to start chapter 6 now. It's actually just a continuation of the things that we were already learning and talking about last chapter when we're discussing fluids and how they move. And we're going to actually use something that's near and dear to my heart, which is watering in a garden, looking at how water flows through a hose and how that's different than some of the things we might have dealt with Bernoulli's idea of the water towers last time. As well as other things like even just how a faucet works, as well as how nozzles on the end of hoses and so on work. So anyway, we have a garden in the backyard that I've spent a lot of time putting in a drip system for and other things. So this is a fun chapter. Anyway, so here's some of the questions we're going to tackle. Some of these hopefully you've already thought about as you've done the in-class work, I hope, for chapter 6, section 1. But anyway, we're going to look at how faucets work. We're going to look at understanding how flow rate is determined, specifically looking at how much changing the size of your hose or your pipe matters. We're also going to talk a little bit about nozzles and how they work, how bends and pipes work, and understanding the noise that water is able to make and where that comes from. So first question, how does a faucet control the flow rate? If we looked just at Bernoulli's idea and some of the things we've learned so far, if you just narrowed the opening like we do on a faucet, it should just make the water keep shooting out faster and faster like a nozzle does. But as you close your faucet, it actually slows the flow rate instead of making it come out faster, eventually turning it off. So how does that work? Well, there's actually something at play here that we haven't discussed, and it's what's known as viscosity. So viscosity is really a fascinating aspect of fluids. It's almost, you can think of it as being more or less like friction in water. So as water particles move past one another in the fluid state, there's a little bit of like friction, viscous forces that slows that motion. Now with water that's not very strong, the viscosity is low, it moves by quite rapidly, but with other things like honey or ketchup or these sorts of things, there's a higher viscosity, and I'll show you a video to kind of introduce this idea in a minute. But anyway, so water travels through a narrow passage in a faucet, and that's part of what causes it to lose some of its energy. So you have this pressure energy forcing water through the pipe, right? This pressure potential energy we've talked about. For many places, it's based on a water tower or an elevated water tank. And that's converted into kinetic energy once the faucet is open and exposed to atmospheric pressure. So that's what's trying to happen. But when you narrow that passage, you create kind of chaotic flows, and you create such a small region that the viscosity, the friction within the water, ends up taking away much of the energy. So the same kind of thing goes like if I take and push or slide, a package across the ground, if we ignore friction, it should just keep going forever, right? Because there's nothing to take away its energy. But since there's friction, that's going to take away energy, and your object would stop not too far after it left. So viscous forces, the viscosity, it's like friction within a fluid. It opposes motion. Again, just like friction, it's always working against the direction of motion. And it wastes energy in the same way that sliding friction does, if you remember when we rubbed our hands together, right? So in the same way, it loses energy, or the viscous forces take energy away from the fluid, either taking away pressure potential energy, or since it's moving, it's going to really be taken ultimately away from the kinetic energy. And so how much that's going to happen depends on a lot of different factors. But one primary factor that it's going to depend on is what's known as the viscosity of a fluid. It's a measurement of how strong the internal friction in the fluid is. Think of it as sort of being analogous to the coefficient of friction with two surfaces. It's like a coefficient of friction, but for a fluid when it's rubbing against itself. All right, so again, this viscosity is a quantification of how strong those are. So if something's highly viscous, high viscosity, it's going to have high amounts of friction. If something's really low viscosity, it's going to have lower amounts of friction. So something like water is going to be low viscosity that doesn't lose a lot of energy to these internal viscous forces. But something, again, like honey or ketchup or molasses, those are things that would have a higher viscosity. All right, so if you think about this, partly because of the viscous forces, the speed at which water moves through a pipe, it's actually going to be slower near the edge where it's being slowed by friction, where than in the middle where there's going to be less of that overall effect. So here's a cool video that these guys called the Science Guys put together testing the viscosity of different fluids. So I'm going to skip part of this, but jump in and we can watch part of their experiment. So that's a good introduction to the idea of viscosity. And one thing you might have thought of as you watch that honey flow, I don't know about you, but if I have honey, I want to get it out, it's not moving very easily. What do? Well, I oftentimes will put it in the microwave for a few seconds, increase its temperature, which will actually decrease its viscosity and increase its flow rate, making it easier to come out. So these viscosity values can also be temperature dependent. So like here's a list of different viscosities that I found from our textbook labeling things like helium at 2 Kelvin. Notice the temperature. So you have to get down to almost absolute zero. And liquid helium is nearly non-viscous, nearly perfectly non-viscous. Air, again, there's very, very, very little resistive force as air particles move past one another. So again, that's nearly a zero viscosity. And then you can see water, olive oil, shampoo, honey. These things, again, have much higher viscosities. But notice we're assuming at 20 degrees Celsius, which is about room temperature for those. As I mentioned, they will vary depending on the temperature. So next question, and I hope you've done this, right? Again, if you've been working here on the in-class worksheet, we're now going to be talking about question 3. I asked you to come up with your own equation. If you haven't done that already, I want you to pause it. I want you to tell me what variables you think will affect flow rate, causing flow rate to be higher, and what will affect them, causing them to be lower. If you imagine you're trying to quantify the flow rate of water through your garden hose. So pause it if you haven't done it already. So if we think about water flowing through a garden hose, the diameter is definitely going to matter, as this question has already implied. It's going to make a big difference, okay? But what other things are going to affect it as well? Well, it's going to be directly affected by the pressure difference. If you have more pressure pushing on your water on one side and less on the other, it will flow faster. As those two pressures get closer together, the difference between the two ends gets smaller, then your flow rate will decrease. So our flow rate is going to be directly proportional to the pressure difference. All right, it's going to be inversely proportional to viscosity, as we just learned, right? Higher viscosity, lower flow rate. So that's an inverse relationship. It should be on the bottom of any equation we have. All right, the length of the hose, the longer your hose is, the more distance it has for friction to take energy away. So one thing I've noticed in my garden, if I have like a 50-foot hose, or even I have these like small, like 10 feet hoses, water comes flying out the end of those. But I have a 100-foot hose, and I've even hooked 200 feet hose together before. By the time you get the water to the very end of 200 feet of hose, it comes trickling out much slower, because the longer the length, the more opportunity there is for viscosity to take energy away. And the diameter, as we mentioned, plays a huge factor. And what you'll see in the equation, diameter is actually to the 4th power. All right, so you get way more flow rate with a small increase in diameter. In fact, when we were building our house, we did all of our own plumbing. My dad was plumbing our master bathroom upstairs, and I asked him specifically to redo one of the hose lines to our bathroom. He was putting in pipe that was a 1/2 inch in diameter, and I asked him to stop, go back, and redo it with 3/4 inch. So only increasing by 1/4 inch in diameter, but that small 1/4 inch increase was going to dramatically increase the overall amount of water flowing to our bathroom, and specifically to the shower in our bathroom. So here's the flow rate equation that we have. It's going to be equal to, again, this is a long complex equation, but we're going to see how we can set different parts of it to constant based on a problem sample we do here in a minute. But flow rate is going to be equal to pi multiplied by the pressure difference multiplied by the hose diameter to the 4th power divided by 128 times the hose length times viscosity. So directly related, the flow rate is directly related to the pressure difference and the hose diameter, and it's inversely related to the hose length and viscosity. Again, directly meaning if those things go up, so does the flow rate. Inversely meaning if those things go up, flow rate goes down. So here's the sample problem I want you to try. And again, this was on our little in-class worksheet, so I hope you tried it out already. But you're told that your friend has a house, and when their house was brand new, the kitchen faucet could deliver 0.5 liters per second. So that's a flow rate. It's a volumetric flow rate, a certain volume, 0.5 liters per unit time per second. So 0.5 liters per second. So dirt and things and minerals can build up inside of your pipes. Our house is only a few years old. I've actually seen that happen a little bit already. And what happens is it can reduce the effective diameter of your pipe. So we're saying that these mineral deposits that have built up over years cause your diameter to decrease by 20%. So, again, if it was 1 inch wide, now it's only going to be 0.8 inches wide instead, okay, across in diameter. So my question is then, what is the new flow rate? That's all I'm telling you. Try it out. Tricky one. Did you pause it and give it a go? Let's try it together. So we have this big complicated equation with flow rate. Just so you understand here, again, FR stands for the flow rate. Here we have our change in pressure. This is our diameter to the 4th. This is our length. And then this is our viscosity, okay? So what do we have here? We have a situation where we're only looking at 2 things that are going to change. The viscosity of water hasn't changed. The length of the pipes in the house hasn't changed. And the pressure difference we can assume isn't changing either. The city is still giving you the same pressure from the local water tower, and atmospheric pressure is the pressure on the opposite side. So the change in pressure is not changing either. So we can put the things that are changing together on one side. So I divide both sides by d to the 4th. So now I have flow rate over d to the 4th equals all of this stuff that we're saying are constants in this exact problem. They're not always constant, but in this problem they are. So the flow rate over the diameter to the 4th power equals things that are not changing. So since that ratio, the flow rate over the diameter, is a constant, we can say that our initial flow rate over our initial diameter to the 4th equals our final flow rate over our final diameter to the 4th. And since it's this new flow rate that we're trying to find, I can multiply this diameter to the 4th, the new one, over to the other side, and it ends up on top because it's on the bottom on this side. This is like cross multiply divide kind of thing going on, right? So what we have then is our new flow rate will be our first flow rate times our new diameter to the 4th divided by our first diameter to the 4th. But I don't actually give you diameters, oh bother. Well, let's see. Our first flow rate we know is 0.5 liters per second. Our first diameter we don't know, but it's been reduced by 80%, or excuse me, by 20%. So I'm just going to choose my original diameter to be 1, and my new diameter to be 0.8, since that's 20% less. So if I do 0.5 liters per second times 1 arbitrary unit to the fourth on the bottom, and then we have 0.8 to the fourth on top, we do the math, and look what we get. Oh, my picture's in the way. So we get 0.205 liters per second as our flow rate, which is indeed box-worthy. Okay, so notice again, you're going to have to practice that on the homework, where you have to set certain variables to constant and then form a ratio that you can then solve for. So here's a thought question for you all, and again, this comes straight off of our in-class work that we've been doing, worksheet. So when water flows smoothly in a straight hose, that water's viscosity causes the water to do what? So this is kind of a recap question. What does viscosity do? Dun, 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 dun. Hopefully what you had guessed is answer D. It's going to cause it to waste energy in the form of thermal energy. All right, so since this chapter is kind of on the longer side a little bit, I think what I'm going to do is I'm going to break the video here so that I can divide this section into 2 separate videos so it's not too long. So take a little break if you want to. Get some water. Make sure you've done the back of the sheet here. All right, make sure you've looked at the back of that, and then we'll go ahead and finish the rest of the video in part 2.